Hello everyone, myself Harish, and this is my project for applied model-based design. My project title is Fault Detection and Isolation in EV Powertrain and Chassis Subsystem. So my project basically consists of four main subsystems: the SOC subsystem, the brake demand and command subsystem, the powertrain subsystem, and the vehicle chassis subsystem. So let me first start by giving the what the actual inputs are to the project. So these inputs are given through a MATLAB file. So here I've defined the vehicle speed, vehicle speed, that is the throttle command, the brake, the vehicle weight, and when the fault has to be triggered, the short circuit faults, thermal faults, and all that have been mentioned here. Uh, so let me just straight jump into my project, and this let me start with the brake and control system. So this is like the brain of the entire project. So this basically has six inputs: brake demand and the throttle command, the thermal fault, the inverter fault, SOC remaining. So this throttle command alone is converted into speed in kilometers using the max speed of the vehicle. And when we go inside, we can see that there are majorly two main subsystems, that is normal operation and fault operation. So under normal operation there are main four subsystems, that is driving, region, blend braking, and mechanical only braking. Driving is used when normal driving condition is there, and when there is a low amount of braking required, region is used. And then when there is a little high amount of braking required, blend braking is used with both mechanical and region. And when there is a high demand of brake or a sudden brake required, so I use mechanical only braking. And when there is a brake failure, a mechanical brake failure, I'm using an emergency region to bring the vehicle to a halt after some time. So there is a faulty case as well, so which the model goes to whenever there is an inverter fault or a thermal fault, and this also brings the vehicle to a stop gradually. And my next the two outputs of the subsystem are pressure command and speed control, which are given to the FOC controller. Let me show that. So the speed command is given to the FOC controller, that is converted into RPM, and this is given to the FOC controller block from the Simulink library. And the inputs to this are current, uh, speed, position, and the DC voltage. So I'm using an 800 volt architecture. So I've used an 800 volt DC, and the outputs are the gate output. So this gate output is given to a three-phase inverter, which is being supplied by an 800 volt battery, and the charge remaining is also taken from this for SOC calculations. And this three-phase inverter has, so this is where my fault triggering and fault finding starts. So this has two switches which are used to trigger open circuit and fault circuit in my inverter. So this subsystem is used for inverter fault finding. Let me go into that. So I'm getting the voltage across the phases as input, and I'm also getting thermal faults as input, so that this inverter fault is not set high whenever there's a thermal fault already. Uh, and also reset command, so that the vehicle can be reset after the fault is cleared. So my initial uh, code sets the open circuit fault high at second 3 and short circuit fault high at second 6. So let's see. So as we see here, our open circuit fault at second 3 is detected, and the short circuit fault at second 6 is detected as well. And I also have a diagnosis where the open circuit fault is diagnosed second 3, and the short circuit fault is diagnosed at second 6. So let me go to the next subsystem. So that is motor, and when this flag is raised, this is sent to the cutoff switch, which uses an OR gate to cut off the switch whenever there's a thermal or a inverter fault. So let me go to the motor faults. And here I've measured all the temperatures and the rate of change of temperatures in all the stators and the rotors, which is then bypassed through a code to raise thermal faults across each of the stator or winding. So let me show the temperature in stator here right now. So I've set fault to trigger at second 14 at stator A. So as you see that the temperature which was around 295 normal operation went very high till 335. Then test I've set the limit of safe temperature at 305. Then when it drops down to 305, it will start working again. That we will see that when I show you the torque and speeds of this. So this is about the motor thermal modeling and fault detection and thermal modeling. So this is about the fault detection and thermal modeling. And here is the torque profile of the motor. As we see, the speed has dropped here. When at 3 seconds when the fault is triggered, the speed has dropped. Then at fourth second the fault has been cleared, so speed raises again. Then at sixth second there is another fault, so the speed drops again. Then when at seventh second the fault is cleared, so the speed catches up to the demand. So this is about the powertrain subsystem in it all. And let me go to the next subsystem, that is the vehicle chassis subsystem. So the vehicle chassis subsystem consists of the vehicle chassis, that is the vehicle body, the gearbox, the mechanical brakes, the wheel, and the axle, and all that. And it also I'm also using a brake failure detection subsystem. So where the inputs are given as pressure command, braking torque, vehicle speed, brake demand, and all that. So this basically compares the uh, pressure command with the braking torque to find if there's a fault between if there is a mechanical error or mechanical fault between the digital control and the mechanical part. So whenever this it finds a mechanical fault, the clutch command is set to low, so that this clutch disengages and disconnects the wheel from the vehicle body. So this happens only when this vehicle is at rest. So before the vehicle is at rest, this does not disconnect. That would cause a danger to the passenger. So only after the vehicle has come to a rest, the clutch is disconnected to avoid any further damages. And this is my sensor fault and calibration part. So I've added a rotational noise to my rotational sensor, and I've measured the RPM, which after the noise is added. So my RPM without zoomed in looks like it's loading a bit. Wait. So my RPM without zoomed in looks like this, without any filtering and all. And my RPM after a EMA filter looks just like this. So this looked better filtered. If we zoom in, we can also see that this is better filtered than the raw RPM value we get from the sensor. So this is one, and this is the speed profile that also matches the motor speed we saw earlier. And this are all the inputs that have been given, the road gradient and the wind velocity that have been given to the vehicle body. And then at last we have the SOC subsystem that is uses the charge remaining and the weight coulomb. This is the total number of coulombs present in the 60 amp hour battery that I'm using, and which is divided and then multiplying it by 100 to convert it into a percentage value that is fed to a brake command control. So this is my entire project and a small overview about the project. Thank you.